So we have a positive voltage of 3 volts, and then we have a resistor. That's what we're trying to figure out, what resistance we need. We have an LED, and we need, in order for the green LED, we need 2.2 volts across that LED. So that just means that we need to have, if this is ground, we need to have 2.2 volts there. So that would mean that we would have, our current going here is supposed to be 10 milliamps. And so 3 minus 2.2 over the resistance that we're looking for has to equal 10 times 10 to the negative third, or 0.8 equals 10 times 10 to the negative third R, or R equals of course it does. R equals 80. Of course it does. 80 ohms. So that's for part A. And part B, do the same thing, just this time we need this voltage to be 1.8. So that would be 3 minus 1.8 over R equals 10 times 10 to the negative third, or what is that, 1.2 equals 10 times 10 to the negative third, or the two places, 120 ohms, that's times R, equals the resistance. Okay, so any questions on that before we look at the next question? And nothing in the chat. Okay.
So is a forward voltage drop, that's just always the voltage on the diode?
Let me see if I understand your question correctly.
Because like it isn't the voltage across a diode usually 0.7, but like for LEDs it can be, I guess, different.
That's right. Yes. For LEDs, it's going to be different because they are a different kind of diode.
Gotcha.
Yes. Yeah, that was a good question and a good point. So let's see if I can do this one. Alright, so we're supposed to use the exponential model to find an expression for V out as a function of V in, and we are given some information. So we have that the IS is 10 to the negative 14 amps, R is 10 kilo ohms, and Vn is 1 volt. So let's see what we've got. We know that the voltage across the diode is right here, that's VD. And we have this voltage across the resistor, so I'll label that right there. We have that we know that it's an op amp, and we know for op amps that I don't know what terminology y'all use. Do you use plus or P for, like, do you say VP equals VN, or do you say V plus equals V minus?
Plus or minus.
Okay, so we know that I minus has to equal I plus has to equal 0, and we know that V plus has to equal V minus, and in this case that would be Vn. And that's just our rules for an op amp. And so if I minus has to equal I plus, which has to be 0, then the current right here has to be 0. So that means that the current through the diode has to equal the current through the resistor. So ID has to equal IR. And V out has to be the sum of the voltages across the diode and across the resistor. And we know from our exponential model that our current through the diode equals IS times e to the VD over VT. And then if I divide both sides by IS, ID over IS equals e to the VD over VT. And then if I take the natural log of both sides, the natural log of ID over IS equals VD over VT. Or multiply both sides by VT. VT natural log of ID over IS equals VD. And then I can say, what can I say? I can say that, well, I know that going back and looking at my op amp, that Vn has to equal V plus, has to equal V minus, and there's no resistor in this branch right here, so that has to equal the voltage right there. And so I can say that VR equals Vn, or that V out equals VD plus Vn. So I can say what do I have here? VD equals V out minus Vn. So VT natural log ID over IS equals V out minus Vn. And so now I can add Vn. So I get V out equals VT natural log ID over IS plus Vn. And I think I have all of these things. So I have V out equals 0.025, which is what we use for VT, times the natural log of, well, I don't quite have all this yet, but I can say that if I look at my my op amp right here, I can say that ID has to equal VR over R, and I know that VR is the same as VN. So ID is VN over R. Plus VN. So now do I have everything? I think I do. Let's see, what do I have? I have no mouse. Yes, it is. It is a constant. Yes. I have R. I have VN. I have IS. Yes. So now I can just plug in. VN was 1 volt. R was 10 kiloohms, so 10 times 10 to the third. IS was 10 to the negative 14. And VN, again, was 1 volt. And I believe, and someone can check me on this, that if you do all of that, you get 1.575 volts. And that would equal your minimum positive power supply, because it can't be the minimum, the positive power supply can't be any smaller than V out. Oops. Okay, any, go back to that. Any questions on that one?
Could you go over how you used ln, that rule real quick?
Just right here?
Yeah, with E, like you got rid of E by using
Yeah,
ln.
yeah. Okay, so anytime you have an equation where what your variable is in the exponent and you need to get the variable out of the exponent, what you do is you take the natural log of both sides, and so well, except you have to have just the base on that side, so ID over IS equals E to the VD over VT. So when you're trying to get a variable out of the exponent, you have just your number right here. Remember, E is just a number. And then you take the natural log of both sides. And then you remember that the natural log is log base E. So this is the log base E of E to the VD over VT. And what log means is what power would you raise this base to get this? And so the power I would raise E to get this is just that exponent. Most people even forget that that's why they do it, and they just know that if you have E to the 5x equals 7, that when you take the natural log, that is the opposite operation of exponentiation. It just undoes the E. It just brings that exponent down. Was that your question?
Yes, yes, it was. Thank you.
Uh-huh. Okay, other questions? All right. Oh, before we do this one, I found some more good true false questions back from the days when I was in this class. So, okay, so if silicon is doped with a donor element, what type of semiconductor does it become? So what do you need to know before you can answer that? No one?
Does it become an N-type?
It does become an N-type. And how did you figure that out? Or if you want to,
Because
okay,
donor gives electrons.
donor gives electrons, and that's what you needed to know. So that'd be N-type. Um, so a p-n junction is where you have uh, p type semiconductor and n type semiconductor right next to each other, but we usually call it something different. What's the more common name for that? No one? That's a diode. What is the common name for a circuit that turns an AC voltage into a DC voltage?
A rectifier.
That would be a rectifier. And then the last one, I had said that earlier I had listed the colors of some LEDs and what voltages you needed for them. Um, find that. Okay, so if I wanted a red LED, I'd need 1.8 to 2.2 volts. If I wanted an infrared LED, I'd need 1.2 to 1.9 volts. I can have that. Green 2.0 to 3.5, blue 3.0 to 3.5, and ultraviolet 3.1 to 4.0. So, which kind of LED is the most common and why?
Is it red?
It's red because it doesn't take as much voltage, and the blue LED took a long time to develop. Okay. All right, so now we can go back and take a look at this problem. So we have a constant voltage drop of 0.7 on our diode, and let's see. First thing we'd want to check is to make sure that the diode is on. And so we have that our op amp is ideal with output saturation levels of plus or minus 13 volts. Assume that when conducting, the diode exhibits a constant voltage drop of 0.7. So we'll assume that it is, and then if we come to a contradiction, we'll figure that out. So we need to first figure out what our relationship is between our input and our output voltage. So does anyone recognize this op amp off the top of their heads? And I never recognize them. I always have to just figure out what they are. So let's see how to figure this one out. So we know our op amps. We have that I plus equals I minus equals 0, and that V plus, which here equals V, is that an I? I think that's I. VI has to equal V minus, which is already labeled for us right there, so that's handy. We know that this current has to be 0, and so we also can do a voltage division on V minus. So we know that V minus has to equal the total voltage change between ground and here, and right there is V out, so it has to equal V out times R over 2R, or V minus has to equal 1/2 V out, and so that's tells us that Vn equals 1/2 V out. Or if we want to look at our gain, which is V out over Vn, multiply both sides by 2. 2Vn equals V out, or 2 equals V out over Vn. So that's our gain. Okay, so now we know that if we have a constant voltage drop, then we have a voltage drop of 0.7 across that diode. So we know what VA has to be. VA has to be, if Vn is 1, why did I assume? Oh, I'm assuming it's 1 because I'm in part A right here. If Vn is 1, then V out, So part A, Vn is 1, then V out is 2, and VA has to be 2.7. And what else are we looking for? V out, VA, and V minus. I think we got them all. Yep. Okay. Any questions on that one? Okay, now if we do part B, we have Vn is 3 volts, so that would make V out 6 volts. Hold on a second. Okay, so part B, there's nothing strange there, so it would be if Vn is 3 volts, then V out would be 6 volts, and VA would be 6.7. But in part C, okay, so I had to go back and review my op amps. So what happens is the diode will not conduct because it is in so Vn is negative. It's -1. And so the diode cannot conduct. So it acts like an open circuit. So that means the op amp is not behaving like it was before, and it is in saturation. If you notice, V negative, V minus, since we don't have anything going on over here, nothing is going on over here, this is 0. So the V positive is less than the V negative. So this is the op amp is in negative saturation. So that means its output VA will be at its negative saturation level. It will be -13. And V out is going to be 0 because all of this is at ground. And the same thing happens when Vn is -3. All the same stuff happens. You'll still have 0 for V out, and VA will be -13. Here's an explanation from someone who knows better than I do. So when Vn is greater than V out, which is what we had in A and B, I mean not greater than V out, greater than VD. So when Vn is greater than VD, so the voltage across the diode, the op amp will attempt to output current to raise V minus to Vn by raising its output voltage. And so the op amp is going to try to get V minus to equal V plus, and it'll do that by outputting current. And that's exactly what happens in A and B. But in situations C and D, the op amp output will attempt to draw current by lowering its voltage. It cannot draw current, so it would attempt to draw current to lower its voltage, but it cannot draw current because of the diode. Therefore, the op amp output will go to negative rail or negative saturation. There's no current anywhere else in the circuit, so V minus equals V out equals 0. So that's what happens there. Just a better explanation. Okay, so for this one, I was so used to the full wave rectifiers that look like this that I didn't pay attention to the fact that it said it has 2 silicon diodes. So in fact, it should look like this. And I don't know if y'all did any like this or not. But I will go ahead and go through it. And then maybe I'll do another one if I have time. Don't know if I have time. Okay, so so this would be what our full wave rectifier would look like. Except this one was 5-to-1, not 6-to-1. Okay, so 2V2, because we have 2 of them right there. 2V2 equals 1/5 V RMS, or 1/5 times 120 volts RMS, or 2V2 equals 24 volts RMS, or 2V2 equals 12 volts RMS, or V2 equals 12 volts RMS. So the secondary peak voltage of the transformer, the secondary peak, if that's RMS, our peak will be 12 times the square root of 2. And so our peak output voltage is going to be 12 times the square root of 2 minus 0.7 from our diode, which is 16.26 volts. So now we want to find the displacement angle between the output and the secondary voltage of the transformer. So we can write that VD equals V2P sine theta, or sine theta equals VD over V2P, or theta equals the inverse sine of VD over 2VP, or theta equals the inverse sine of 0.7 over 12 times the square root of 2. Let me get my calculator in degrees. Do I want it in degrees? Yeah. No, I did not want it in degrees. I want it in radians. And I get that theta equals 0.08259 radians. So now, to get the conduction angle for a full cycle, I'm sorry, first we need to get the conduction angle for each cycle. So the conduction angle is going to be pi minus 2 theta, or pi minus 2 times 0.08259. Which is 2.976. And now to get the conduction angle for a full cycle, that'll be 2 times the conduction angle, which will be 5.95 radians. And then to get the fraction of the cycles in which the diodes run, well, there's 2 pi radians in a cycle, and so I'll take theta c comma f over 2 pi, or 5.9 over 2 pi. And I get 0.947, but that is for both diodes, and so, or 94.7%, but that's for both diodes. So for each diode, it's, you take that, divide by 2, and you get 47%, 47.3%. And so the fraction of each cycle is 47.3%. And now to get the output voltage, we can do that by looking at our circuit. And I'm just gonna be honest here and say we didn't do this in my class at all. Nothing like this. So I really don't know what's going on, and rather than trying to figure it out and just mess it up, I have a solution here. This one goes with a version that's slightly different. I think the one that I posted had a 5-to-1 ratio. And this one had a 6-to-1 ratio, so their number is slightly different from the one that I just got a second ago. But I will leave this up here, or you can pause it if you want to see how it works, because I can't say that I can explain it right now. So So let's see if I can try. So V out, so we're using KVL, VP sine phi minus VD. So let's take a look. So if we do a KVL around here, so V is changing, and so V is at any given point its peak voltage times the sine of phi, where phi is just an angle. It's not any particular angle. It's just saying that phi goes from 0 to 2 pi. I mean, this is just oscillating, and we have so if I took plus V out and then plus V out, yep, so it would be, if I did it all in one line, so going around like this is going all the way around like that. So plus V out, and then minus V2P sine phi plus VD equals 0, and then take those to the other side. V out equals V2P sine phi minus VD. And then to get the average value, you integrate over a period. So the period would be 2 pi. And so integrate from theta to pi minus theta. So we're integrating from So if you look at what's going on in this particular circuit, diode 1 conducts, and then diode 2 conducts in this dotted line. They're showing VS, and our conduction angle is what goes from the parts where D1 is conducting. So apparently if I knew more about how this worked, I would understand why. But pi is right here, and pi minus theta is right there. So that's pi minus theta. So then we will integrate from theta to pi minus theta, 1 over 2 pi and this is how we earlier, or maybe you haven't yet, I don't know, but this is how you get the average value over here. So you would integrate over the angles here where it is conducting, and there's two of them, so that's, I imagine, where the 2 comes from. And then you integrate. That actually is something I could do, but that's just math. And then you get the average value. And then to get the average value of the output current, you would just use Ohm's law.